Hello everyone. Today we'd like to present our project, Speech Emotion Recognition Using Deep Learning. Here's a quick outline of today's presentation. First, we'll begin with an introduction to our project. Then we'll introduce the datasets we used, and after that we'll explain the architecture of our deep learning model. We'll then show you a short demo video of our system in action. And finally, we'll wrap up with some conclusions. As you know, emotion plays a critical role in human communication, and understanding emotions helps machines respond more naturally and effectively. Our goal in this project was to build a model that can detect emotions from voice recordings using deep learning techniques. For this project, we built a custom dataset by combining audio files from multiple open source emotional speech datasets. The two main sources we used were RevDes, which contains high-quality English emotional speech recordings. The second one was EmoDB, which includes German speech samples with various emotional expressions. From these datasets, we selected a subset of 5 target emotions: angry, happy, neutral, sad, and surprised. We also combined datasets across languages to enhance the diversity and robustness of our model. In our project, we focused on building an effective and accurate model by gradually developing 4 different models, each designed to improve upon the previous one. To start off with our first model, we built a simple CNN-based classifier. First, we extracted Mel spectrogram features from each audio file. This converts the audio into 2-dimensional image-like representation, which works well with convolutional neural networks. Then we designed a basic CNN architecture. So it has 2 convolutional layers with ReLU activation and max pooling. After flattening, we added a fully connected layer with dropout to prevent overfitting. And finally, we used a softmax output layer to classify the input into 5 emotions. This baseline model achieved moderate performance, but struggled with class imbalance and showed signs of overfitting. So in the next model, we focused on improving generalization and handling data imbalance more effectively. First, we normalized the Mel spectrogram input, and we also computed class weights to handle imbalanced emotion classes. Architecturally, we added batch normalization layers after each convolution to stabilize learning, and dropout layers to reduce overfitting. These changes helped our model generalize better and improve the test accuracy. And this model served as a foundation before moving on to more advanced architectures using LSTM. For our third model, we combined both CNN and LSTM to build a hybrid architecture. So we first extracted MFCC features, which represent short-term spectral patterns and are commonly used in speech processing. Then we used a 1-dimensional convolution layer to capture local patterns in the time dimension. This helped us extract short-term acoustic features like pitch or energy changes. And after convolution and pooling, the output was passed to an LSTM layer, which allowed the model to understand the temporal evolution of emotions. And like before, we applied batch normalization and dropout to regularize the model. This hybrid approach improved performance compared to pure CNN or LSTM, as it captured both spatial and sequential information from the speech data. For our final model, we built an advanced hybrid architecture that combines CNN, bidirectional LSTM, and attention mechanisms, along with several enhancements in data processing and training strategy. So we started by extracting MFCC and Mel spectrogram features and concatenated them to form a 40-dimensional feature per frame. To improve generalization, we applied data augmentation techniques such as time stretching and pitch shifting during pre-processing. The model architecture begins with a 1-dimensional convolution layer to extract local acoustic features, followed by a bidirectional LSTM and an additional LSTM layer to capture long-term and bidirectional temporal dependencies. We then applied an attention mechanism, allowing the model to focus on the most informative parts of the time series. This was followed by global average pooling, a dense layer, and finally the softmax output layer. This comprehensive approach, combining advanced architecture, data augmentation, external data integration, and adaptive learning rate, yielded the highest test accuracy among all our models. Now we'll show you a short video of our model in action. In this video, you'll see how our system takes a voice recording as input and predicts the emotion behind it.
Kids are talking by the door. Kids are talking by the door.
Kids are talking by the door. Kids are talking by the door.
Kids are talking by the door.
Das schwarze Blatt Papier befindet sich da oben neben dem Holzstück. Das schwarze Blatt Papier befindet sich da oben neben dem Holzstück.
In 7 Stunden wird es soweit sein.
Heute Abend könnte ich es ihm sagen.
From the results, we could notice 2 key phenomena. First, we trained our model using English datasets and tested on German speech samples, and the accuracy dropped significantly. However, when we trained the model with German data, the performance improved noticeably. This clearly shows that the language of the training data has a major impact on emotion recognition accuracy. And initially, we assumed that a model trained on English would generalize well to other languages. But in reality, factors like intonation, speaking speed, and the way emotions are expressed vary between languages. So this made cross-language emotion recognition much more challenging than what we expected. So one of our conclusions is that language-specific training data is essential for building effective and accurate emotion recognition systems. So thank you for listening, and please feel free to ask any questions.